Welcome back to Kinetics. In part 2 of this video, we are going to be looking at reaction rate and how that relates to the concentration of reactants or products in a reaction. Let's go. So reaction rate is the increase in molar concentration of a product per unit time. It can also be expressed as the decrease in molar concentration of a reactant per unit time. So either the product is increasing in concentration or the reactant is decreasing in concentration. So we're going to be looking at this example, or at this reaction over the next course of this. 2N2O5 makes 4NO2 plus 2 oxygens. If we denote molar concentration using brackets, in other words, this is the same thing as saying molarity in units of moles per liter, then the change in molarity of oxygen will be represented as delta bracket O2, meaning the change in the molarity of oxygen, the change in the moles per liter of oxygen in the container. Then in a given time interval, delta T, the molar concentration of oxygen would increase by delta O2. So the rate of the reaction would be given up by the formation of oxygen is the change in the concentration of oxygen for the change in time. Now, since oxygen is a product, the change in the concentration of oxygen should increase. In other words, oxygen should get larger and larger because it is being produced over time. The equation gives the average rate over the interval delta T. So if we were to graph the concentration of oxygen of that product compared to time, oxygen would start at nothing because it's a product and hasn't been produced yet. And over time, oxygen would increase and increase and increase and increase as time went on. So that's what this graph is about. Now, if we wanted to find the average rate of production of oxygen, how quickly is oxygen being made over the course of this reaction? So we're going to take the change in the concentration of oxygen over the time interval that we're looking at. For example, if we wanted to find it over this particular time interval from, looks like 600 to 1200 seconds, then the change in the concentration of oxygen is 0.0015. So the rate over this time interval is 0.0015 per 600 seconds, or 2.5 times 10 to the negative 6. If I wanted to find the rate of production of oxygen over a different 600 second time interval, let's say from 4200 to 4800 seconds, this particular time interval, then the change in concentration is 0.0003, and so the rate would be 5 times 10 to the negative 7. Notice that it's 5 times 10 to the negative 7 up at the end of the reaction, and 2.5 times 10 to the negative 6 at the beginning of a reaction. So that at the beginning of the reaction, it's actually being produced much quicker than it is at the end of the reaction. And you can tell by the slope being more steep at the beginning of a reaction and more shallow at the end of a reaction. This is because as the reaction is going on, the products are decreasing and decreasing and decreasing in concentration. So since there's not as many products, they can't make reactants as quickly. So this is how you could find the average rate. I could find the rate average over the entire course of the reaction, starting at 0 and ending at 6,000 seconds by saying it changed by 0.0078 moles per liter of oxygen over 6,000 seconds, and then I could determine that rate. But what if I wanted to find the rate at a particular time, the instantaneous rate? So, for example, in this graph, I want to find what the rate of the reaction is at this particular time. Looks like 2400 seconds. Well, you can't take a rise over run if you've only got one particular spot, because there's nothing to subtract from or nothing to add from. So in that case, we're going to draw a tangent line to the graph at that point. So at this point, we need a tangent line. So the tangent line has been drawn, and the tangent line was drawn much better before I put my pen to it. And so you're going to find the change in oxygen from that tangent line. Let me take my line off, and you can see the change in concentration of oxygen from this tangent line itself. From here to there, that's the change in concentration, and from here to there, that's the change in time. And then you can find the instantaneous rate, the rate at an exact given second. Now you can also relate the rate of a reaction to the stoichiometry of the reaction. So again, this was our reaction from the beginning a couple pages ago. Now we want the rate of formation of oxygen, that's what we had already been talking about, That's the change in concentration of oxygen per time. The rate in formation of a product is the change in the concentration of that product over time. If you wanted the decomposition of N2O5, then you would have negative the change in this reactant over time, because reactants are reacting and they're going away, and so the change in that would be negative, and the negative will negate the negative. We can also say, based on the stoichiometry of the reaction, that there are 2 N2O5s to make every 1 mole of oxygen. So let's say I started with 4 moles of N2O5, I would end up with only 2 moles of oxygen. In the same amount of time it would take me to get rid of 4 moles of N2O5, I would only produce 2 moles of oxygen. So if I wanted to relate the rate of formation of oxygen to decomposition of N2O5, I would need to double the amount of oxygen. That seems weird, because the 2 is on the N2O5, and there's not a 2 on the N2O5 in the rate. And the 1 is on the oxygen, and now there's not a 1 on the oxygen in the rate. We've switched them. We made them backwards. But we made them backwards for a good reason, because in the same amount of time it takes to make 4 moles of N2O5, we're only going to make 2 moles of oxygen, so I would have to double oxygen to say that that rate produced is the same as the rate of N2O5 decomposed. Let's consider the decomposition of nitrogen dioxide, a gas that causes air pollution. Nitrogen dioxide decomposes to nitric oxide and oxygen as follows. And suppose a particular experiment, we start with a flask of nitrogen dioxide at 300 degrees and measure the concentrations of all three, the nitrogen dioxide, nitric oxide, and oxygen, as it decomposes. The results of the experiment are summarized in this really nice little chart here and this beautiful graph. Notice that the nitrogen dioxide starts high and the oxygen and NO both start low, because the oxygen and the NO haven't been produced yet at the beginning of the reaction, and the NO2 has not started going away. Over time, NO2 goes away because it's reacting to produce nitrogen monoxide, or nitric oxide, I guess, and oxygen. So those two get higher and higher as time goes on. Notice that the NO curve is taller than the O2 curve, showing that for every 2 moles of NO produced, there's only 1 mole of oxygen produced. So the first question we've got is, relate the rate of decomposition of NO2 to the production of NO. So I'm going to kind of erase some of my markings here so it makes it easier to look at. So let's see. There are 2 moles of NO2 decomposed for every 2 moles of NO produced. So it looks like the rate of NO2 going away should be the same as the rate of NO being produced. Let's check it out how it looks in the chart. Over the first 50 seconds, NO2 goes down by 0.0021. Let's see, 0.0100 minus 0.0079 equals 0.0021. And notice in the same amount of time, the NO goes up by 0.0021. Showing that NO is produced just as fast as NO2 is decomposed. So you can state that in that particular sentence, NO is produced just as fast as NO2 is decomposed, or you can say negative rate of NO2 is equal to the positive rate of NO. Meaning that the rate of NO2 decomposed is the equal and opposite to the rate of NO being produced. If we wanted to look at the rate of production of NO compared to oxygen, notice that on the graph, NO is much higher than oxygen because NO is produced twice as fast as oxygen is produced. For every 2 moles of NO that are produced, only 1 mole of oxygen will be produced. And kind of the chart shows us that 0.0021 of moles per liter of NO are produced and 0.0011 moles of oxygen are produced, which is about half. There's a little bit of experimental issues here. So, for example, by 300 seconds, we'd gotten 0.0062 moles of NO, but only 0.0031 moles of O2. O2 is produced half as fast as the NO is produced. And so for that statement on number 2, you can say O2 is produced half as fast, or NO is produced twice as fast as oxygen. Or you can write mathematically saying that the rate of NO produced is twice the rate of oxygen produced. Notice that I've said twice the rate of oxygen, even though in the reaction the 2 is in front of the NO, because I would make one oxygen for every 2 NOs, so I would need to double the oxygens to equal the same as the number of NOs. Next we've got find the average rate of decomposition of NO2 over the first 50 seconds. Alright, try this one on your own. Right now, get a pen, get a calculator, and find the average rate on your own. Pause your video now. Alright, did you pause your video? I hope you did. I paused long enough to go get a calculator and grab an orange, and let's get started. We're going to find the average rate of decomposition of NO2 over the first 50 seconds. Let's look in the chart. I'm not going to look on the graph for this one because there's really nowhere on the graph for 50 seconds, so I can't really tell what the concentration of oxygen is over the first 50 seconds, even I've got that right. Oh, there's the point on the graph. It's right there. No, I'm not even sure. So anyway, I'm not going to use the graph for this because I can't tell where 50 seconds is on the graph, but I can certainly tell where 50 seconds is on the chart. So if we said that the rate of decomposition of NO2 is equal to negative delta concentration NO2 over delta T, then we have negative, and final minus initial, so 0.0079 minus 0.01 divided by 50 minus 0, change in time. That gives me negative 0.0021 over 50. And since it's a negative, then it ends up being a positive. And here's a hint, rate always has to be positive. You're always going to make a certain amount of something. You can't ever make negative amounts of any chemical. So 0.0021 divided by 50 is equal to 4.2 times 10 to the negative 5. If we look at units, which are really important, 0.0079 is molarity, minus 0.01 is molarity. This is the concentration in molarity, divided by seconds, 50 seconds minus 0 seconds, so this is molarity per second. Alright, now we're going to find the rate of decomposition of NO2 at a particular time, the instantaneous rate at 100 seconds exactly. So here I'm going to take 100 seconds, and look on my chart exactly at 100 seconds. There we go. So exactly at 100 seconds, I cannot do the same thing I did before, which was the change in concentration of NO2 over the change in time, negative, because I don't have a change. I have one particular concentration and one particular time, and I can't do a change from that. I'm not looking at the average rate over the entire reaction, just that particular time. So that's why there's a tangent line. So let's look at that tangent line. Notice this tangent line that was drawn to the curve right there. And so that tangent line goes up by 0.0024, and it goes over by 100. So the change in concentration is 0.0024, and the change in time is 100. And that's molarity, and that's seconds. And one thing is that change in concentration is negative since the NO2 is losing, so it's actually negative 0.0024, which makes it overall positive, and I get 2.4 times 10 to the negative 5 molar per second. Let's do another one. Find the slope of the tangent line at t equals 250 seconds on the NO curve and at t equals 250 seconds on the O2 curve. I want you to work this one on your own. Pause the video now, and I'm going to go finish my orange. Well, that was a good orange. I hope you paused the video and finished your snack and also found the slope of the tangent line at time equals 250 seconds on the NO and O2 curve. So let's see if we can work this out. 250 seconds should be about here. If we go 250 seconds up, we get to a point on the oxygen curve, and if we keep going up, we get to a point on the NO curve. And so we want to find the instantaneous rate at 250 seconds. So they have for us drawn this beautiful tangent line right here and another beautiful tangent line right there. That particular tangent line has a rise of 0.0015 and a run of 150 seconds, not 250. And this other tangent line has a rise of 7.5 times 10 to the negative 4 and a run of again 150 seconds only. So the slope of the tangent line is the change in the concentration of the thing divided by the change in time, or delta y over delta x. And so I end up with 0.0015 molar per 150 seconds, not 250 seconds. The tangent line is centered at 250, but it's only 150 seconds long. And that gives me 1 times 10 to the negative 5. If I do the exact same thing for oxygen, and I've got 0. Oh wait, no, not 0. Try that again. 7.5 times 10 to the negative 4 molarity divided by 150 seconds. That gives me 5 times 10 to the negative 6 molarity per second. All right, did you get those right? Ooh, hopefully you did. So now we're going to relate the ratio of the two slopes to the balanced equation. So let's again look at those two slopes. For the NO curve, that was 1 times 10 to the negative 5. And for the O2 curve, 2, 3, 4, 5 times 10 to the negative 6. So notice that the O2 curve is half the slope of the NO curve. The slope is half, showing that the O2 is produced half as fast, or the NO is produced twice as fast. The ratio of the two slopes is a 2-to-1 ratio, saying that the NO is produced twice as fast as the oxygen is produced. Okay, and that's all we have for reaction rate. Join me next time when we get to talk about mechanisms. Oh, what fun!